Okay, can you see the slide on the screen? Right, thank you. Okay, we have discussed the concept of absorption coefficient and absorption depth yesterday. Right, so and I think by now you should have understood that in order for you to have complete photons absorption, so assuming the illumination from the sunlight, for example, so you should have enough thickness of your semiconductor material in order to do that, right? So this is also applicable to other light sources as well. For example, if you are using monochromatic light to shine on your semiconductor material. Ya, saya tengah sapu meja ada tiba-tiba banyak semut pula pagi ni. I don't know why. If you're shining, for example, a monochromatic light with single wavelength, for example, at 600, at 400, so the same principle applies. Okay, so you need to know the incoming wavelength, the incident wavelength, and then what's the typical thickness required in order for you to ensure complete photon absorption, or else you will raise some photons not absorbed, and therefore it will not contribute to the current. Okay, so later on in the second half, you're going to learn that, for example, if you're working on optoelectronic semiconductor devices like light sensors, solar cells, photo detectors, you're going to see that the photons absorbed by your semiconductor material, whether it's crystalline silicon, amorphous, organic, or some other inorganic semiconductor materials, the photons absorbed will be proportional to the current that you can produce by the devices. Okay, for example, if you absorb little photons, then that's going to result in little current from the device. Or on the other hand, if you absorb most of the photons, that's supposed to translate into a higher level of current from the device. Okay, so whatever you absorb is what you are going to get as a current from the device in the second half later on. Okay, but that's the underlying principle. Okay, so that's why when you talk about a device like a solar cell, for example, you want to absorb as much photons as possible so that you can produce as high current as possible. Okay, high current means a higher conversion efficiency of your solar cells or your solar panels, right? So you're going to see the details later on in the second half. But this is the underlying principle: photon absorption or light absorption. So let's move on to the next concept, which is generation rate. So remember, we are now discussing generation and recombination. And generation essentially means generation of generation of carriers in your semiconductor devices. But if you're generating using light, for example, light absorption, then we normally call it as photo generation or photo generated carriers. But if you're using electron bombardment or high voltage or some other mechanism, then you don't call them as photo generated because the carriers are not generated by photons. Okay. Tapi kalau you punya method of generation is by light, then you can call them as photo generation process because you use photons to induce generation of carriers, free carriers in the conduction band. So generation G is the greatest at the surface of the material where the majority of the light is absorbed, as we discussed yesterday. So let's recall that the blue photons will be absorbed near the surface, if you talk about greens and yellows, they're going to be absorbed, slightly in the middle of the volume of the material, and red photons are typically absorbed at the back. So the sequence or the order is the order of absorption is the shortest wavelength is absorbed first, or the highest energy photon is absorbed first, followed by longer wavelength or middle energy, if you like, and followed by at the back the longest wavelength or the lowest energy, right? So remember the equation Fada shared yesterday, that the photon energy is the inverse of the wavelength, right? Planck constant times speed of light over the wavelength. So we'll give you the energy of the photon. So G rate or generation rate gives the number of electrons generated at each point in the device due to absorption of photons. So we're talking about generation of photons specifically here, but it can also be related to generation of carriers by some other mechanism. Okay, this is more on the solar cell. So that means what this point is trying to illustrate is, if you have a crystalline silicon or some other semiconductor material, your generation rate will give you a number of electrons generated at each point. It can be here, it can be there, it can be there, it can be there, it can be at the back, it can be on the side. At each point in the device due to absorption of photons, if you're talking about light generated carriers. But if you're talking about some other mechanism, then it's going to be a bit different, okay, because it's not wavelength dependent. So neglecting reflection, if you assume reflection is 0 for light generated carriers, yeah, now we're talking about light generated carriers. The amount of light which is absorbed by a material depends on the absorption coefficient. So assuming if your photon incident does not result in any reflection, for example, which is not the case in the real life, so assume that your R is 0 ataupun tak ada reflection lah. So will you ever get a surface with R equal to 0? What do you think? Or any surface with R close to 0 perhaps? What would this surface look like by your current understanding? If your surface gives you reflection close to 0 perhaps, how the surface would look like? Any idea? Based on the optics that we learned a few days back and your previous knowledge? Any opinion on this? Will it be fully transparent? Okay, how would it look like to your eyes? If you're saying the R is 0, how would it look like to your eyes? Can you give any example, perhaps? Ataupun, how does it look like? Fully transparent means you can see through, right? Just like our Windows, for example. Even our Windows has a transmission of about 85% or 90%, and that's still not fully transparent. There's still about 10% of reflection and absorption lost, and that's what you get. So, any ideas? If a surface gives you reflection of 0 or close to 0, how would it look like? Ataupun apa yang what do you get to see? Now, I'm trying to okay, Hassan said a mirror. Well, why do you say why did you say mirror, Hassan? Okay, Bala said a black surface. Right, this is interesting because on one hand, we have a mirror as an opinion. On the other hand, we have a black surface as an opinion. What do you think? Maybe you can elaborate a bit, Hassan. Can you unmute yourself and share? Let's discuss. Boleh, Hassan? Bala, would you like to unmute yourself and start? Let's get opinions. And let's discuss.
Usually, black surface and object, black color in nature is said to absorb all light. So, as opposed to white, which it reflects all the wavelengths of light. So, black absorbs all the wavelengths of light. So, I was thought maybe a black
Hmm.
surface.
Right, interesting. All right. Okay, right now listening on this side. Okay, Hassan, no worries. Okay, so Bala said, Bala compared white surface and a black surface. And he said a white surface reflects all the light and a black surface absorbs all the light. Okay. Okay. On the other hand, Hassan said a mirror. A mirror. Okay. Let's go into the first point first. A mirror. Uh, what is the job of a mirror? What is the role of a mirror? What do you expect when you are in front of a mirror? When you're standing in front of a mirror, what do you actually get? Anyone? Maybe some ladies here would like to share. When you are in front of the mirror, what do you expect to see? And why is it the case? Anis, Anis Shabira, would you mind sharing? Can I unmute yourself? Okay, we got some points here. Reflecting light, to reflect light, shiny surface, reflection, light reflection, your own image. All right, good. So, so good. So those points, in summary, if you're standing in a mirror or in front of a mirror, does the mirror have to be a good reflector or a good light absorber? A good reflector, right? You want to see yourself, isn't it? Kalau you tiba-tiba satu hari you hari siang, you stand in front of a mirror but you don't get to see yourself. What do you think? What's going on there? Hari siang, tengah hari you tengok dekat cermin, you don't get to see yourself. It's in a horror movie already. You don't get to see yourself. So something's wrong already, right? Somewhere, I don't know. No actual image for light to reflect. Mirror dimension. Yeah, it could be mirror dimension. Tapi kalau you standing in front of a mirror but you don't get to see yourself, something is really wrong, isn't it? Yeah, something horror going on already. I don't know. Right? You have to see yourself because a mirror is supposed to reflect the light. So you can check out for yourself. A typical mirror should at least reflect 80% or 90% of the incident light. That means whatever comes light yang you ada dalam bilik ataupun from your ambient, from the outside, for example, supposed to hit the mirror and get reflected into your eyes and you get to see yourself. That's why you learn in optics, isn't it? Kalau you don't get to see yourself or you see yourself in a weird shape, perhaps, so that means the mirror dimension has some issue there, roughness or textured or fractured, perhaps. Just like the way typically you see yourself in a fun fair, isn't it? Kalau you masuk rumah hantu, you get to see something, weird shape, kurus ke, I don't know, gemuk sangat daripada typical. So that means something's wrong somewhere, or it's manipulated somehow, right? So a mirror is supposed to reflect the light, and it's supposed to give you high reflection. And the same goes to white light. So you want to you want to wear a white shirt to reflect most of the light so that you don't feel hot. On the other hand, as Bala said, if you have a black surface, it's supposed to absorb the light, all the light, or virtually all the light, or virtually all the incident photons, and absorbing most of the incident photons means you're gonna get reflection close to zero. Okay, so that means going back to this question, you're gonna get R close to zero when you have a black surface. So you can check this out if you wanna read more on the blackest surface on Earth created by mankind, check out Vantablack, which is essentially carbon nanotubes, right? I think created by University of Surrey or Essex. I think Surrey in the UK, right? You can check that out. When we are working on research on black silicon as well in USM under my team. We're trying to convert the shiny silicon into a black surface so that we can drive reflection to be close to zero and absorption to be close to 100%. Okay, so that's what it means. So kalau R0 means black surface, R close to 100% or 1 if you like, if you're going to convert to 1, is a white surface or as a mirror. Okay. So neglecting reflection, the amount of light which is absorbed by a material depends on absorption coefficient, which is alpha, as we discussed previous class. And we also discussed about the depth, which is 1 over alpha, absorption depth. And the thickness of the absorbing material. So you need to have sufficient thickness in order to absorb most of the incident light, right? The intensity of light at any point in the device can be calculated according to the equation. We talk about the 30%, 36%. Absorption depth, right? The point which the intensity is left at 36% when compared to the original intensity when the photons hit the surface of the semiconductor material. So differentiating I, if you differentiate the I, you're going to get the G. We'll give G at any point in the device. So the G, or the generation rate, is then equal to alpha, absorption coefficient, times N naught, photon flux at the surface. So flux at the surface is N naught, if you like, there at the surface. And here is when you go into the device. X, increasing X on the X-axis here means going deeper into the material. Okay, so you can take this picture and itu balikkan. So sini akan jadi surface lah. Photon hit the surface there. That will be your N naught, which is there. And then this one is going into the device, going into your material, right? So that's like 300 micron furthest on the right. N naught and exponential to the power of alpha, absorption coefficient, and x, the distance into the device. And that will give you the generation rate of this shape. Okay, they can exponentially reducing generation rate into the device. The simple model for the recombination generation mechanism states that the net recombination U is proportional to excess carrier density. So whatever you have as your excess carriers will lead to proportional occurrence of recombination. So whatever you have, so the more carriers you have in your material, in your device, is expected to lead to higher recombination accordingly. So it has to be proportional. No net recombination takes place if the semiconductor is at thermal equilibrium, because we learned before that G equals to R. Okay, and if you want to say net recombination is U, then this is essentially U. Okay, for small disturbance that is low injection, the expression for the net recombination rate of electrons in a p-type semiconductor is given by U, net recombination U, which is equal to NP minus NP naught over tau E. Okay, NP minus NP naught. So this is where the understanding of the thermal equilibrium condition versus the new condition comes in. So that will give you delta N, which is the excess carrier density that you just created by the low injection or the high injection or middle injection condition, over tau E, the lifetime. So tau E is a minority carrier lifetime. So kenapa dia minority carrier here? Any idea why is it minority carrier that we are interested in? Remember last time we talked about low level injection where it only changes the minority carriers, right? So it doesn't change the level of the majority carriers. Okay, So if you're talking about N-type semiconductor, then your N will essentially be equal to your N naught because delta N is just too small, assuming low level injection. But however, it's going to change the minority carriers, isn't it? So delta P is small, but P naught is way smaller, and therefore it's going to be approximated as delta P. So we discussed last time that if you're talking about low level injection, it's not going to change the majority carriers, but it will change the minority carriers. So therefore, we are interested in minority carrier lifetime. That's the reason, okay? Because it's going to change the minority carrier total after the injection. And similarly for holes in an N-type semiconductor. So bila you cakap tentang minority carrier, then we are talking about the opposite carrier to the majority carriers. For example, if you're talking about N-type silicon, so assuming this is my N-type silicon. So what is the minority carrier in this device that we are concerning about, the minority carrier lifetime? Holes. So you want to know the holes lifetime in this N-type semiconductor. Okay? Because the low-level injection only changes the minority carriers. Kena faham majority carrier versus minority, because when we talk about PN junction, starting from this weekend onwards until next week, we are going to talk about minority carriers a lot. And you're going to see parameters like NP. You're going to see parameters like PN a lot. PN not, NP not. Okay, apa maksud NP? NP is density of electrons in p-type semiconductor. What is PN? Density of holes in N-type semiconductor. Ini banyak student buat silap. So the moment you are seeing this opposite alphabets, if like PN or NP, then you are talking about minority carriers already. Okay. NP is density of electrons in p-type. PN density of holes in N-type. Okay. Dua benda, two items that you have to mention: density of electrons in p-type, density of holes in N-type. So let me just test you one thing. If NP is density of electrons in p-type, then what is NP naught? Anyone would like to give a definition on this? NP, you should have two things. If you're talking about NP naught, you should have three things. N, one is for N, one is for P, one is for naught. Okay. Can someone define what is then NP naught? You have to get this clear before moving on. Anyone? What is then NP naught? Anyone?
Density of electrons in p-type semiconductor in thermal equilibrium.
Exactly. Good. Three things. Okay, kalau kita sebut NP, density of free electrons in p-type material. That's it. Done. NP naught, density of free electrons in p-type semiconductor or p-type silicon, for example, gallium arsenide, whatever lah, at thermal equilibrium. Okay, three things. Means when you're asked to define or you're asked to calculate and calculate PN naught, calculate NP naught, calculate PN, calculate NP, you should understand this first. If you're clear about this, then the rest, the following will be easy. Kalau you're not clear about this, the rest will be messy. Okay, so good, Bala. So what is then PN naught? Can someone else other than Bala help to define? I want to get this embedded into your mind first before we continue. What is then PN naught? Someone? I like to get it explicit so that everyone is clear. Let's get it loud and clear. Kuatin, would you like to help on that? What is then PN naught?
Density of holes in N-type semiconductor at thermal equilibrium.
Brilliant, good. Three things: density of holes in n-type semiconductor at thermal equilibrium. Okay, good. So kalau you have questions on calculate PN, so it's just density of holes in n-type semiconductor. Understood. I don't have to define, because some questions don't define all the time. Okay, so you have to understand that. So now it's explicit, loud and clear. I want everyone to understand that and not miss it, right? So clear. Nanti moving forward, when we talk about PN junction, majority carriers, minority carriers, your holes originally from p-type now crossing to n-type, and then the holes now become a minority in n-type. You then have to calculate the minority in n-type. On the other hand, electrons crossing into p-type, now the electrons become minority in p-type. You then have to calculate the minority electrons in p-type. All this will come back, right? So that's why we have to get it loud and clear first, right? So minority lifetime is interested in minority because of this discussion, right? It changes the minority carrier concentration, but it doesn't change the majority carrier concentration. Okay, so UH is therefore Pn minus Pn naught over tau H. Sama macam kat atas. Net recombination rate for hole at the bottom, net recombination rate for electrons at the top. So which will give you delta P over tau H. Okay, so then if you look at this equation, UH equals to delta P over tau H, you can tell already that UH is proportional to delta P. UE is proportional to delta N. So that is what this sentence is trying to convey. The net recombination rate is proportional to the excess carrier density, whether they are electrons or whether they are holes. They will be proportional to the net recombination rate of either one, right? So when the optical generation is suddenly switched off, now you let's just imagine that you are shining your silicon with light, and then the light is suddenly off. The carrier population will tend to return to their thermal equilibrium values over time by the process of recombination. So that means bila you ada silicon and then you turn on my office light, for example, then you are instantly generating excess carriers. And of course, that depends on the intensity and the wavelength of my light in the office, if you're talking about indoor generation. So then you're going to have some delta P or delta N accordingly, right, in this material. Tapi the moment I turn off my light in the office, or ataupun you block, you put your sample in a black box, you close with a black light, black cloth, then tak ada lampu masuk langsung, even diffuse light from the surrounding, it's not coming in at all. Then at that point, the carrier population that you just generated, delta N or delta P, will return back to the thermal equilibrium values. It will go back to your N naught and it will go back to your P naught. But this will take time. Maksudnya bila they drop, it's not going to drop instantly. This one is on and then this one off. Dia tak adalah instantly like square wave macam tu. It's going to drop like that, right? So this is time factor on the x-axis. So it's going to decay. And this is called recombination process. Okay, recombination process. So they can relax to its thermal equilibrium values. We're going to see later, right? So relaxation to thermal equilibrium. You used to have delta N plus N naught, delta P plus P naught, depending on your P type or N type material. And then you turn on the light. So then lights on, if you like, here. And then at this point, lights off. Okay, and then you're going to have your carrier population decay to its thermal equilibrium values. So it used to be P naught, and then when the light is on, it's P naught plus delta P. And then when the light is off, it's back to P naught. Okay, so that's what it means. So, and this process along the way is recombination. That's why we are interested in the recombination rate, which is given by delta P over tau H. And if you do dPdt's negative U, or net recombination rate, right? So recombination, what is then recombination? Recombination is a process where the thermally excited electrons drop back to the valence band and recombine with holes. They akan combine balik. Remember last time we talked about breaking a bond in order for you to thermally generate free electrons in the CB and leaving free holes in the VB. So that is generation process. You break the bond, the electron is excited into the CB. Now electron is coming back to the annihilated. Okay, annihilation process. Annihilation process. Annihilated. Okay. Recombining lah. When you see annihilation or annihilated, so that means recombining or they recombine with each other. Electrons lose energy and stabilize back to the VB, recombining with hole. This process called recombination. There are three basic types of recombination in semiconductor. So remember last time we talked about electrons going up to the CB, and this is generation process. Kena clear ni, huh? G process, generation process. And the inverse coming back to the VB is R, recombination. Generation going up, recombination coming back down. And there are three types of recombination processes that you may have in your semiconductor material. You may have one, you may have two, you have all the three, right? The material depending on the condition of material, condition of the device, injection level, processing that you use in order to produce the semiconductor material. Many factors. We're going to see each of them in the next explanation, right? So the first one is called radiative recombination. We learn a little bit about this when we learn about direct bandgap semiconductors, where your electrons from the CB losing energy and recombine with the hole in the VB, and that recombination process emits photons, right? Emits photons, and emitting photon, emitting light is called radiative recombination process because it involves light emission. Okay, light ataupun photon. That's why we call radiative. The radiation, radiation. On the other hand, the second one is called Shockley-Reed-Hall recombination, named upon the persons who discovered Shockley-Reed-Hall recombination, and this recombination is due to defects. If you have defects, if you have imperfections, if you have impurities in your materials, in your devices, you are always going to have SRH recombination. Okay. The third one is called Auger recombination. Okay, the way we pronounce is Auger. Ada anyone taking French? Auger recombination. So we're going to see this one later on. So it involves three particle process. So it's not only involving E and H, but it involves three particles process. Apa maksud three particles? Let's see. Okay, on the next few pages. So recombination can occur by three main processes. The first one is radiative. Radiative is also called band-to-band. Sama, if you see band-to-band or radiative, is actually the same thing. Oh, sorry, it's actually the same thing. And the second one is SRH, or also called trap-assisted. Trap means tempat where the carriers are trapped due to defects. That's why we call them as trap-assisted recombination. And the third one is Auger recombination, which involves three particles. So these three particles can either be two electron plus hole. We normally call it as E process, EEH. It can also be one electron, two holes, process. Kalau nak ingatlah, E process, process, EEH and EHH. So either two electrons or two holes with the opposite one. So in this particular case, we're talking about two electrons and one hole. So let's see why is it the case. Okay. So they occur in parallel independently, hence their recombination rates are additive or superposition. So in your crystalline silicon or gallium arsenide, indium phosphide, cadmium telluride, zinc oxide, you may have one, you may have two, you may have all. depending on the materials, processing, defect levels, and direct or indirect band gap. So that will determine whether you're going to have which mode, right? Only band-to-band is radiative. The other two, SRH and OJ, are non-radiative. So only the first one, in this case, in this schematic, is the third one, the C, the one in C. Only band-to-band is radiative. Only this one emits photons. Yang ni je yang emit light. The other two do not emit light. So you won't have lights from SRH. You won't have lights from OJ. No light, no photon emission. Hence, they are called non-radiative. Only one is radiative. So radiative recombination, this is the inverse process of electron hole pair generation. So we talk about generation going up, recombination is coming down. A CB electron, a conduction band electron, falls into the VB hole, giving up excess energy as light. Okay, this is also referred to as band-to-band recombination and radiative recombination. Sama aja. So this radiative recombination properties is exploited in optoelectronic devices where you need to emit light. For example, LEDs, lasers is the most important application in direct bandgap semiconductors. Okay, so we discussed about direct bandgap last time, so that's why the concept is very important. So where your conduction band minima is aligned to your valence band maxima, and then your electron is going to drop into the VB, emitting the light, emitting photons. And this is only happening in direct bandgap semiconductors like gallium nitride, gallium arsenide, and whatnot, right? It's not possible in crystalline silicon because of its indirect bandgap nature, unless you change the indirect bandgap crystalline silicon to direct bandgap by going for quantum dots, for example, right? Detection of radiative recombination is the basis of photoluminescence imaging. If you are working on a PL in your FYP, so this is based on the principle of radiative recombination. Okay, so essentially this. That's why you get to see the light. You can then tune your light emission to blue, green, red, white, or some other colors that you can see from LEDs, for example. That's the basis. Radiative recombination depends on the density of available electrons and holes. Yep, we discussed this now. Both karyotypes need to be available in the recombination process. The rate of recombination is expected to be proportional to the product of N and P. So the more carriers you have in your device, the more radiative recombination you're going to get. At thermal equilibrium, the net recombination rate must equal to the generation rate, since there is no net recombination or generation, and that will be equal to this equation, where B is a bimolecular recombination constant. Okay. So how about non-radiative then? So we learned that out of the three, two of them are non-radiative, SRH and OJ. Okay. SRH is due to defects, and OJ is due to three-particle process, especially when the doping level is high. How high? Let's say non-radiative process, also called SRH, named after the scientists Shockley, Reed, and Hall, discovered in 1953. It's like 70 years ago, right? Impurities and defects result in deviations of perfect lattice. So you're supposed to have a perfect lattice, but when you have impurities, especially unintended impurities, remember we learned about this concept in the very first week of this class, unintended impurities and defects in the lattice result in crystal imperfection, which are called defects, right? So these causes allow energy levels to be in the forbidden gap. You're not supposed to have any energy level in the forbidden gap because it's forbidden to begin with. But then due to the presence of defects, the defects are physical in nature, but electronically, they are states in the band gap. They will present as states in the band gap. which are not intended. Okay, not intended. Defect level near mid-gap are the most effective recombination centers. So the moment you have states in the gap, in the forbidden gap, they will present as recombination centers. Because here they are going to suck your free electrons into the states and then followed by recombination with a hole in the valence band. So these occurs via a two-step process as shown below. So the first step is your free electron will be trapped by the trap state there in the middle, for example. And then the second step is your electrons that is already trapped by the state will be dropping to the VB and recombining with hole. It's a two-step process. Okay. Especially in indirect bandgap semiconductors when you have crystal imperfections. Okay, kalau you don't have this crystal imperfection, then you are not going to have this SRH recombination. The excess energy is given to the lattice as heat when you have this in the indirect bandgap. Because in indirect bandgap, remember last time we talked about the difference when this drops to the VB, you are going to have phonon heat to the lattice instead of light because it's not it's not a direct bandgap semiconductor. So surface of the crystal is a defect. Give range of state at surface within the bandgap. This can be very effective recombination set as well. For example, if you're working on a sample, kalau you want to sample FYP, or you sample FYP, say this is your sample, my sticky notes. So if you have some defects that you can see or even cannot see, kadang-kadang some defect you can see by your visible by your naked eye. Some defect you really have to go under the microscope in order to see what are they. Some you really can't see them under the microscope, but you have to really go under the SEM, for example, to be able to be visible, right? The defects on a sample, kalau you nampak something tak elok on a sample, they are potentially defects, and they are potentially recombination centers, effective recombination site. So kalau tiba-tiba you buat FYP, you dapat sample very ugly ataupun tak uniform atau it looks very weird, it looks nampak tak cantik lah, tak cantik is a sign of defects punya presence, for example. Some are really robust, some sample. Tapi generally, kalau you suddenly dapat bintik-bintik or something that you don't intend to get, they are potentially defects. Okay. Suddenly you do IV measurement and then you get nothing out of it. So those are potentially the reason why you don't get your results. Okay, due to SRH recombination. So let me finish in the next few minutes. No, 10:49. So SRH recombination occurs via bulk defects or trap, same thing. You don't have to worry about this equation. The single trap recombination can be described as electron capture or hole capture. It can capture both electrons and holes. The net recombination rate for trap-assisted recombination, if you want to go into the details, and these are the things. These are the equation that you have to work on to be able to calculate the net recombination, right? And the same goes to the following one as well. Okay. The third one is called OJ recombination. Let's finish off with OJ. It's a non-radiative recombination process, and it involves three particles. Can either be EEH, 2 electrons, 1 hole. Can also be 2 holes, 1 electron. Okay. Only one conduction band electron recombine with a hole and passes excess energy to the second electron in the CB. So that means when you have OJ, if you're talking about EEH, so what happens is the first electron recombining with hole in the VB, and the recombination, the energy difference is passed to the second electron And this second electron is then excited further up into the CB. And this is Auger recombination. Okay, so this is EEH process. On the other hand, for EHH, it's also possible where the recombining electron passes the energy to a second hole in the VB. And the recombination, the energy difference is passed to the second hole, and this is excited further into the VB. It's not up lah, but then it's further into the VB, further down if you like, further down. Tapi sebenarnya dia into the VB lah, walaupun you see that as going down. The excited second carrier is called hot carrier. This is called hot carrier. This is also called hot carrier. Hot carrier ni kita guna in the device, for example, in solar cell and some other devices, to be able to harvest the energy difference due to the hot carrier. If you talk about solar cell, then we label or we call this concept of this or this mechanism as hot carrier solar cell. Harvest the energy difference there as your output of the solar cell. So it's called hot carrier solar cell. Can you hear me now? Because I'm seeing fluctuation in my internet. Just checking if you can see. And now can. Right, tadi ada problem Sorry for that. I just realized a fluctuation. So the process most important in heavily doped semiconductor. So you are going to get this Auger in heavily doped semiconductors only, typically above 10 to the 17 or highly excited material. So if you're talking about moderately doped, lightly doped, you are not going to have Auger recombination. Okay, let me finish with Auger, and then today's what, Thursday? We're gonna finish off the remaining for this lecture on Saturday, and then we're gonna move on to PN junction equilibrium. So Auger recombination involves free particle. It can be EEH or EHH, right? The transition is as we discussed on the previous page, right? So the expression in terms of the net recombination due to Auger is given by this equation. Okay. Ini pun sama, but then this is high level injection. You don't have to worry about this. Just an example for you. Yeah, I think let's just stop here. So today we have covered the concept of generation rate, which is the result of differentiation of intensity, okay, intensity of the light incident on a semiconductor, and then relaxation to thermal equilibrium, and then the concept of recombination process, which can be divided into three types: radiative, Shockley-Rittal, and Auger recombination. So in any semiconductor material that you work on, you may have one, you may have two, you may have all the three, depending on the condition. For example, let me just give you one question before we finish. Let's see. Okay, let's say you are working on gallium arsenide with a perfect lattice, lightly doped. Gallium arsenide, perfect lattice, lightly doped. Which type of recombinations do you expect in your material? Gallium arsenide, look at my criteria. Gallium arsenide, satu, perfect lattice, lightly doped. Based on your understanding from this lecture. Okay, let's see. You can write down your answer here. Zol said radiative. Bala said radiative. Okay, Zul and Bala just radiative. Kenapa radiative? Would you mind to explain? Zul, can you explain? You said just radiative, okay? Kenapa just radiative? Can you explain a bit so that we can recap the concept? Zul or Bala, would you mind? Yeah. You can unmute yourself.
It doesn't have any defects, so it cannot be. Forgot the second one. What's it called?
SRH?
SRS, yes, and
Yeah.
it's only lightly doped, not heavily doped, so it cannot be auger, I think.
Yep.
Auger.
There's
So
OJ, right? So
yeah,
why is it radiative then?
because it's direct.
Direct band gap, right?
Yes, direct band gap. Yes.
Yes, good. Thank you. So gallium arsenide, perfect lattice, lightly doped. Gallium arsenide is direct band gap, therefore you should expect radiative. Perfect lattice, no defects. There's no SRH. Lightly doped, there's no OJ, so just radiative. Let me give you another example. Okay, before we conclude this recombination mode. You have crystalline silicon full of defects, lightly doped. Crystalline silicon full of defects, lightly doped. What are the recombination modes do you expect? SRH, just SRH, yeah? Any other opinions? Crystalline silicon full of defects, lightly doped. So Bala said just SRH. Any other opinions? We have 3 more minutes to finish. 2 more minutes. Let me finish off in 1 minute. Just SRH, right? Crystalline silicon is an indirect band gap, no radiative, full of defects, therefore SRH, lightly doped, no OJ. So therefore just SRH. Last example. Cadmium telluride, direct band gap, okay? Or perovskite, direct band gap. Perovskite is an indirect band gap, so direct band gap semiconductor. Perovskite, no defects, heavily doped. Perovskite, no defects, heavily doped. What do you expect? Which one do you expect of the three? Perovskite, no defects, heavily doped. Radiative and OJ, right? Any other opinions? Ada? Correct, good. So perovskite is a direct band gap, therefore radiative is expected. No defects, therefore no SRH. And then heavily doped. Heavily doped means easily more than 17, therefore you should expect OJ recombination as well. So therefore, the answers are radiative and OJ. Okay, good. So that's how you test yourself. You can test with various range of different conditions, and then you come back to the principle. Radiative is based on direct or indirect. SRH is whether you have defects or not. OJ is dependent on the doping level of the material. If you are exceeding 1017, you should expect OJ. If you're not exceeding 1017, you shouldn't expect OJ. Or perhaps if you're close to, you probably be seeing a little bit of OJ coming out, right? So that's all for today. I hope you understand what we learned from today's concept. So I'll see you Saturday 10 to 12, right? So we're going to move on. We're going to finish off with this topic, and then we're going to jump right into PN junction at thermal equilibrium condition. So don't forget your assignment 1 is due tomorrow by 5, and then be prepared for your test 1 next week, 8 to 10 p.m. Thursday, isn't it? Right? So I'll see you then Saturday 10 a.m. Bye-bye. Take care. Assalamu alaikum.